Okay. All right. So, yeah. So does that make sense for everyone up to this point? So is it a good time to go to the next part? All right.
Oh,
Perfect. So you see how we found the charge concentrated at this point with respect to this surface, right? The excess total charge is just asking us, okay, what is the charge enclosed at this central point with respect to this surface, the charge at the same point with respect to this surface, and you just take the difference of those. That's pretty much what it's asking. So, like we did for this inner radius, we can do the same exact thing for this outer radius. And, I don't have to really do all this math again. It's going to be the same exact thing mechanically, right? So you can say Q enclosed inner, say, yeah, in for short. That's equal to, and we just take this same thing here, epsilon E, or let me write the cleaner version of 4 pi epsilon E. Oh, and E1 corresponds to the inner radius. That's the electric field strength at that radius with respect to this point where the charge kind of, accumulates. So E1 and R1 squared. And okay, for Q enclosed outer, it's the same thing. Like I said, mechanically, same math. So without writing all of this, we're just going to get 4 pi epsilon, those are constants. And then E2, we're not doing E1 anymore. That's, specific to the inner one, just to remind. And R2, right? Because R2 goes to this outer sphere squared. So I will write over here Q excess. That's just Q enclosed out minus Q enclosed in. So that's really just 4 pi epsilon E2 R2 squared minus E1 R1 squared. Clean that up. And that is what you are supposed to get. There will be numbers probably in the problem, and all you do is just plug them in. Don't remember this. This is what you need to remember, this whole process. If you can recreate this, which there of course will be a video for it, um, you'll do really good on this problem. There's going to be a problem just like this on the test. Oh, I see someone asked, do we need to solve for E1 and E2 or will they be provided? Um, they are provided. Yeah, they will be provided. If that reassures, yeah, yeah, they're not gonna just. I mean, if they don't give it, then this is the best form to leave it in. So that's the first problem. Anybody have any? Oh, I see more questions. Wouldn't the center charge and charge on the surface of the inner cancel? Not necessarily. No. So, I guess do I understand that question? Center charge canceling with the surface charge. Yeah, no, they don't really cancel. So what's going on is you have a charge here and a charge here, on opposite ends or sides of the sphere. The shell, I should say, the spherical shell. And this is just empty space. The reason that there's an enclosed charge here is because it the charge kind of concentrates given the geometry to this central point. So if let me know if that answers the question or um yeah, point charge in the center. Oh, no. Yeah, specifically in this problem, this is just an imaginary central point where the charge happens to uh, condense, for lack of better wording. So maybe I should put right there no particle. Yeah, this problem will be uploaded. I just now started recording, but would you guys would do you need me to go over this piece briefly again, or is that okay? Because I will admit I did not get to record that little piece. I forgot to hit the record button. Anyone? All right. So if no one has anything for this problem, if this makes complete sense, I can jump to the second one. Am I good to go? Perfect. All right. So now we have this setup. Three particles. We have a charge here. Oh, forgot to write the charge for this particle. We have two charges known.
Can you move the page down a little bit?
Oh, yeah. Thank you. So we have,
Thank you.
what was that?
I just said thank you.
Oh, you're welcome. So, oh, I think I'm just hearing my voice echoing. So you have two charges that are known. This is just Q. So we have an unknown here, and we have a potential at this point, right? We know the distance between these 2 points, the distance between these 2 points, and the first thing we want to find is what is Q? So since we have a bunch of, you know, details, numerical information, and we have a potential, most likely it'll be smart to use the equation V equals Q over R, right? The equation for potential. And okay, when there's collective potential, you're just adding the potential from this particle, the potential from this particle, the potential from this particle. There's no negative potential. Well, when we're considering all of them collectively, what gives the potential polarity is the charge itself that it's attributed to. So instead of this, we get a slightly more complex but still simple version. We get Q over or K and Q, let's say QA over RA being the distance between A and this reference point, QB over RB. Oh, Jesus. Okay, let me write that a little better. QB over RB, same thing, distance from here to here. And QC over RC, right? And okay, QB, we don't know what that is, so that's just Q. And essentially, we want to plug in numbers and move things around to isolate this right here. That's all we have to do for this first part. So I'm gonna go ahead and do that. The way I like to do it is to not plug in anything first. I like to plug in later. So the first thing, it's V over K, move that to the other side, divide, blah blah blah. QA over RA, we know what that is. So we subtract from this QA over RA, and then QC over RC, we know that as well. QC over RC, and that leaves us with Q over RB. And yeah, it's just basic algebra. You just move this to the other side, right? Let me, yeah, there we go. So now this turns into RB times V over K minus QA over RA minus QC over RC. And that is what will be equal to Q. Now, given this, right, we can start with QC. I'm just looking at the first thing that, I'm just going off of the first thing I'm looking at. RC is given to us. Let's say that's 4 centimeters away, so that's 0.04 meters. And okay, RA. RA is just, it's just whatever this distance is. So that will be 0.03 meters. And here's a diagonal. How do we do that? Well, Pythagorean theorem. So RB is just, the square root of RA squared plus RC squared. And, plugging in those numbers. Oh, 3, 4, 5. That's just going to be 5 centimeters. So 0.05 meters. So that's RB. Okay, now we can plug into everything. So 0.05 meters times the potential is 3300 volts divided by K. What is K? Never remember what K is. Um, okay, for the sake of laziness, I'm just gonna leave that as K. You guys know what to do with, yeah. So I'm bugging. That's 8.99 times 10 to the power of 9. Correct me if I'm wrong. I'm better with the mechanical part than remembering constants. So QA, right? QA is given to us, that is 5 nanocoulombs. So that's 5 times 10 to the power of 9 coulombs divided by, you have RA right here, 0.03 meters minus the same thing, but just, for particle C. So yeah, with negative 5 nanocoulombs, that negative turns this negative into a plus. So 5 times 10 to the power of 9 coulombs over our C is 0.04 meters. So we will put that 0.04 meters. And okay, I don't feel like reaching for a calculator, but oh, wait, hold on. I thought mine was somewhere else. So, okay, I can just plug this in right now. 0.05 times. And you guys, I encourage you to do this as well. Don't have to, but you know, let me know what number you get just in case I miscalculate something. Oh, one thing, nanocoulombs. Okay, that those nines are negative. Yeah, make sure not to make that mistake. And if you do, catch it. Oh, just now saw this. Isn't it to the negative 9 for the charges? Yeah. My bad. Yeah, I made sure to fix that. And then the number that I get at the end is, did you guys get this? 1.6 times 10 to the power of negative 8. Or I guess, for whoever might be doing this at the same time. Oh, okay, good. You got this as well. All right. And that is part one. Part two. Let's say you have a test charge. It's just like a little, a particle with a charge that you're putting at this point. What would the potential energy be? Actually, it's pretty simple because we know that. Oh, where did I put this? Back to the formula sheet, we have this handy dandy little thing right here. And another way to write that is just, U equals QV. So if it's true that U is equal to QV, then the potential energy will get, let me draw a line right here. Let's say, okay, the test charge is 1 nanocoulomb, so 10 to the power of negative 9 coulombs times 3300 volts. If we if that formula is true, which it is, but if it's true, then you should get, okay, let's see, 10 to the power of negative 9 times 3200. You should get this. Oh, what was the power on the answer? Uh, oh, which answer? For the first part or the second part? First, okay, that's 8. Let me write that better. Is that more? Okay, I guess, yeah, yeah, I see it right here. It's easier to read. All right, so did anybody else get 3.3 times 10 to the power of negative 6, joules for the second part? I might be going through this quite fast, so I can give you guys a second actually. Oh, okay. Sean got it. Did anybody else get that same answer? The 3.3, me box in the answers. All right, perfect. So, any questions? This is, like I said for the first problem, this is very similar to what you're gonna. Yeah, that's all we had to do for part two. If you can do all of this, hundreds for the second question.
Could could you go over that second part? Sorry, I was still writing like the first one down, so I kind of
Oh,
missed what you
oh yeah,
said.
yeah, yeah. No problem. So, what it's asking, they might ask it in some weird, obscure way, but if you can catch what they're asking, they're really just saying, oh, here's a potential. There's a point with its distances from each of these particles. Here's a point with a potential, right? Let me actually, here's a potential right here at this point. Let's say you take a particle, slap it onto that point, and let's say that particle has a particular charge. What will be the potential energy from the perspective of that particle? And, potential energy is just uh, charge times potential. So you just plug and chug into that formula and you get this answer.
Okay, did they give us the sorry, I can't really like see the question or
Oh,
statement for part B, but did they give us like the charge or like how did you get 10 times 10 to
yeah,
the
they'll give us a test charge.
Oh, it says 1 nanocoulomb. Okay, I see it now. Yeah.
Oh, yeah, I see someone asked, where did the 10 to the power of negative 9 come from? Oh, yeah, that's, you mean this one, right? This one, Alex?
Yeah. Oh, I was confused on that.
Yeah, yeah, yeah. So that's just I'm just converting to SI units. I'm just going from nanocoulombs to coulombs. But are there any other questions? Feel free to ask anything. Any question is welcome, of course. You guys give me the signal to go to the next problem. All right, that's oh cool, cool. That's five, more than five people. All right. And of course I can go back to anything. I can go back to any problem. So if I progress to another one and there was something from another one you had a concern on, I will go back. All right. So here we have the third problem. You guys can see that. All right. Okay, maybe this might be hard to read. I'm gonna be talking through it. I'm not gonna expect you to really read too much. So another problem that I can't say too much, but you're more than likely gonna find it on the test is this one. You have a potential given with respect to x and y, positional parameters. And the first thing that it might ask you is what is the electric field magnitude at x equals 3 and y equals 2, for example? And then it'll also probably ask you to find the electric field at that position, but the direction of it, the angle. So, that being said, I'm going to go straight into, let's say, part A, right? So, there is this. Actually, before I do anything, do you guys, are you familiar with the gradient? Did Leila Body or Aktash teach you guys about the gradient? You know, this thing right here where the gradient of f is just, you have x component, y component, take the derivative of f with respect to x, and then, now in the y component, you take the derivative with respect to y. They didn't teach you guys that? Okay, one guy, Alex, says no. Does that make sense as, just a mathematical construct? Would it confuse you guys if I used this in the problem? This is just a vector of derivatives that are with respect to each component.
I know Layla Body covered it in one of his lectures.
Okay. Um, okay, I guess I like to use the gradient because it's just, is this the method they look for in the test? You don't have to use the gradient. So here you see these equations on the formula sheet. Ex equals negative derivative with respect to x of potential, and then with respect to y of the same thing, with respect to z of the same thing. And all this means is that you're just putting these derivatives in a vector. That's all. I just like to use this, for shorthand, but if anyone is confused, I can, do it the other way as well. But what each of these, a generalization of each of these formulas is that the electric field is equal to the gradient of potential, which means if we write this out in vector form, here we have an x and y component, so we don't care about z. We don't need to think about it at all. So a vector, and then okay, in the x component, we yeah, you can do it both ways for reference. Um, so in the x direction, you have the derivative of v with respect to x, derivative in the y component, derivative of v with respect to y, And okay, we have something to take a derivative of. So let's just do it. With respect to x, you have negative 10y cubed. That looks horrible. Negative 10xy cubed, 30x squared minus 10 to the power of, or 10y cubed. And as far as x is concerned, because we're just taking the x derivative, as far as x is concerned, y is a constant. Negative 10 on that y, another, we're just dealing with constants on this side of everything. So you take a derivative of something that's constant, you get zero, right? Because a constant doesn't change. So we're just really taking the derivative of this 30x squared. So, basic derivatives, you bring 2 to the front, subtract 1, that gives you 60x. And same thing in the y direction. 30x squared, all of that is a constant. That does not change with y. So if we're taking the derivative with respect to y, we're only concerned about this negative 10 and this exponent. So bring to the front, subtract 1, blah, blah, blah. Negative 30y squared is what you should get. Does that make sense to everyone so far? Like suggested, I will do it without the gradient because that's just, I don't want to confuse you guys. To whoever didn't really like learn that. So that being said, there's an x, there's a y. So it's important to remember that the electric field is a function of x and y. So I'm just rewriting this. I'm just bringing this over here, just putting it there. 60x, not 6x, 60x, and then minus 30y squared. And then, okay, what is the electric field magnitude at x equals 3, y equals 2? So, perfect. We have an electric field vector. We just have to find the magnitude. We're just going to use Pythagorean theorem. X component, y component. We have a right triangle, conceptually. So, that's just, oh, let me do this. So we have this vector, and okay, I'm using, I don't know how to call this, naked notation. This is the same meaning as this, but it's the magnitude. That's why it doesn't have the arrow. So E as a function of X and Y is equal to, right? This component squared, so 60 squared, well, 3600 X squared, and this component squared, so it'll be plus 900 y to the power of 4 because it's already squared. Let me clean that up a little bit. All right, does that make sense so far to everybody? What I'm doing? Well, I'm just gonna go ahead. If anyone has any more questions, just let me know. Okay, so find electric field magnitude at this point. X equals 3, y equals 2. All you have to do is just plug into that. So I mean, I'll just go ahead and do it. So that should be, well, I'll just do that in the calculator. All right, 36 times x is 3, right? Y to the power of 4. Okay, times. And then what you should get is 216. If I didn't mess up any numbers, that's the right answer. So I'll just put that right there, 216. And, since we did everything with SI units, this answer should come out with SI units. So that'll be nano, or not nano per coulomb. It'll be newtons per coulomb. And okay, direction of electric field at that position. This this shouldn't be too hard. So what I'm gonna do is okay, A should specify that, be specific. Okay, now we have B, right? We have this vector right here. So to find the direction of a vector, you just we have this, tangent of theta is equal to an opposite length and an adjacent length. And then, okay, you want to find the angle? Easy. Just find the arc tangent, or in other words, the inverse tangent for both sides. And, inverse tangent of tangent just gives you the argument of tangent, the angle. So we take the inverse of this, inverse tangent of L opposite, L adjacent. And okay, these are just going to be the components of this vector. So let's say, okay, just to make it a little more visual for whoever learns like that, you have this angle, right? And then, okay, up is y, x is horizontal, and then cool, right? That just means that, okay, what's opposite is y to this angle, and what's adjacent is x. So I'll just put up, adjacent, Jesus. All right, opposite, adjacent, right? And what we're gonna do is, okay, you have 60x negative 30y squared. So we just take the y component, put it here, x component, put it here. So you have the inverse tangent of ey over ex. And that would give us inverse tangent of, okay, what is ey? Ey is negative 30y squared, and then 60x. And it's asking you to do that at this specific point. X equals, let me make these bold as a matter of fact, 3, 2. X equals 3, y equals 2. So we just plug and chug, right? So inverse tangent of y equals 2. So that's negative 120 divided by 3, right? 180. And okay, back to the calculator. Wait, what mode am I in? All right, degree mode. Perfect. Okay, let's see. Okay, what I got is this, assuming I was perfectly correct with, plugging in numbers, which is this really the part I be messing up. It's really the numbers. I can do like the mechanical part, but I plug in numbers and I forget a negative and mess stuff up. So, okay, if I didn't mess anything up, hopefully you guys also got negative 33.69 for that problem. Any objections? Anybody, everybody agree with that? Oh, and specifically degrees. Perfect. Great. And oh, well, uh, if everyone was able to, if everyone can recreate this, that would be, you got hundreds for everybody, unless you mess up a little negative somewhere, a little number. But if if you can recreate the same logic, don't remember the result, don't remember the equation, whatever equation I derive. Please remember the process. If you guys can do that, we'll be in pretty good shape. Can you explain again why the magnitude was 216? What do you multiply? Oh, so what I did with the magnitude was I I have this vector, right? Let me know if that assuming that that answer makes sense. I just took this component, I squared each and added them, put a squared root, rooted them, and then for x and y, I just plugged in this information that's assumed in the problem. It's given. If that answers your question sufficiently. Perfect.
Could you just restate the problem for A? Because I can't read it and I didn't hear it.
Oh, yeah. So you have this expression in terms of x and y for the electric potential, and they want you to find, I want you to find, because I'm not going to tell you exactly what's on the test, but the closest I can get is for part A, what's the electric field magnitude at, x equals 3, y equals 2. So, at this P equals 3, 2, right? And okay, what is the direction of the electric field at that position? So there will be a vector, an electric field vector at that point, and they just want you to find the angle for it.
Okay, that makes sense. And also, what if you had it like also in the z direction? Would you just also take like the partial derivative of z also? Like,
Yeah,
would it be the same thing? Okay.
exactly. I mean, you can look at it this way. So you have, so you have y, x, and z. Since there's nothing in the z, it's just flat. Whatever has happening is on a plane.
Okay, that makes sense. Thank you.
Yeah, no problem. And someone wanted me to do this without the gradient, right? You still want me to do that?
Yes, please.
All right, perfect. So, okay. Let's see. Actually, let me not misremember that. 30x squared. And always let me know if, I'm writing too small because I just habitually write small. What was that? 10. Okay, 10 to the power of 10y to the power of 3. And then, okay, it's asking for electric field magnitude, right? So here we have the formula sheet and, oh, I blanked for a second. Here we have this, right? So just write them here. Ex equals negative dv, negative. I always forget negatives. dv dx, same thing, ey equals negative dv dy, and you asked a great question, by the way. Some might, someone on this planet probably thinks it's a stupid question, but it's actually a very precise question. Yeah. So, like I said, there's no, it's nothing going on in the z direction, so we can ignore that. And all right, so we solve for e, the x component of e, right? So the negative derivative with respect to x of this entire thing, 30x squared, and this, and then, okay, like I said, uh, the derivative of this is going to be zero because we only care about any change in the x-axis because the derivative is a rate of change. It entails change. If we're concerned only about change along the x-axis, we don't care about what happens on the y-axis because you have the x-axis here, y-axis here, you have a point. Imagine it's going up and down. If you project that onto the x-axis, nothing happens. So there's that. Just to explain a little bit of little precise detail. So, with that being said, just ignore this. That means nothing to us right now. So, derivative of this, what to do. You have the negative, just leaving that negative in front. 2 times 30x, and then there's negative 60x. And you do the same thing in the y direction. Imagine a point just dancing side to side. It's the projection on the y-axis is going to be the same. So d dy 30x squared minus 10y cubed. There's a negative in front of this. Don't forget about that. Please don't make my mistakes. This is a constant. This doesn't matter. We're taking a derivative of a constant of a non-changing value, which means that just goes to 0. So you have the negative from here, they cancel out. So the answer should be positive for this derivative, which means that we can just say, okay, bring the 3 to the front, it's 30y squared, right? Uh, what is it asking? Field magnitude, electric field magnitude. All right, so you have an X, you have a Y. I just, what I was trying to say earlier was this. That is, yeah, that's not on the formula sheet, but I hope that's like intuitive up to this point. I'm assuming that to be intuitive. If it's not, then just let me know. But assuming that this can be true because it's Pythagorean theorem, plug and chug, expression for this, expression for this. Ex. Okay, negative 60. The square of negative 60 is the square of 60. 3600. Oh, 3600 x squared. Right. Oh, wait. Yeah, x squared. Okay. Y component is 900. Y to the power of 4. And what I did was I just plugged in numbers. I believe P was equal to 32. 32, so that just means that 3600 times 3 squared squared. And what I got from that was 216 newtons per coulomb. And okay, now okay, that's A, B. Direction of electric field at that position. Well, like I said, there's this point P. There's a vector situated at that point. So, the vector has its components. And if you want to find that angle, you have to take into account the fact that the tangent of that angle is just the opposite over the adjacent. So opposite being this, the y component, yx, ey over ex. And then you do some magic right here, I guess. Some theta is equal to inverse tangent of this to the power of y, e to the power of, no. So e sub y, e sub x, oh, oops. And then I just, plugged and chugged and started plugging in numbers. But do you want me to go to completion with this, or does that make sense of how I ended up with this? Like, do you need to, is this all you need, or would you like me to start plugging in numbers and stuff? I can do anything. As a matter of fact, I only really used up one of the 2 hours. This
One
is
question I was struggling with was the two charges hanging at a small angle from each other.
what was
Like
that?
trying to find the distance between the charges.
Oh, wait, are you asking about this one?
No, I know there's a blab on it. It's like if you have two charges hanging, they kind of form like a triangle. And there's
Oh,
they
kind
kind of
of
looks like
like
a cherry, I guess. Like two cherries.
so you have a pivot point, I guess, two
Yeah.
tangents, and then boom, boom. Right, is that what
Yes.
you mean? Yeah. So what about that?
Trying to find the distances between, like the distance between them.
Oh, yeah, yeah, yeah. So luckily, that won't be on the test.
Okay. Will like any part of that like type of problem be on there at all?
Not at all.
Okay.
Like I said, these problems that I just went through, they're like really similar to what you're going to see on the test.
Okay. There's like five questions, right? So it's
Yeah,
okay.
and oh, yeah, that's why I have three. Yeah, because the other two I did them in recitation. Does anybody need me to go over those again?
Yeah, could you go over those again, please?
Yeah, the recitation problems.
Yeah.
All right. Yeah, I can do that. Let me find them. Okay, here we go. Yeah. So these are just my notes, but I'm gonna just look at them as I'll get a piece of paper actually. All right. So, oh, okay, sorry. You asked the question of like, will there be something like that? Yeah, there will be like a problem that's like half of that problem, but not exactly two particles. That's what I meant to say. So, yeah, just number one of like the recitation problems was you have this, say that particle is discharge. Let's say 15 degrees. That's just, vertical. And there's an electric field. And, well, actually, let's say we're given a value, right? I'm gonna just use the same thing as the recitation. 2 times 10 to the power of 5 Newton coulombs or Newton per coulomb, Newtons per coulomb, right? So 2 times. And very importantly, Jesus, Q does not move. This is Q. Q, Q does not move. All right, so um, three things you're gonna want to find for a problem like this, whether you have two particles or not, kind of dangling, respect to each other like a triangle, like you said. Uh, Free body diagram, we would want to start with that. So, and the benefit is that it makes you really think of all the forces involved. Because off of the top of your head, sometimes you'll forget a force. So here we have the gravitational force. And okay, the electric the electric field lines are going this way. So where are they gonna go if the charge is negative, given that F is equal to QE?
The opposite way.
Perfect. Opposite way. So it's going here, then the force will go this way. So electric force, and there's a tension force, right? That's why this is not falling. That's why this is staying still, because you know of these forces. If it wasn't for this string, it would just go this way, or it'll accelerate this way. So must take into account the tension force. All right, so what does it ask? So yeah, free body diagram. Okay, boom, we have that. So I guess that would be part A. Part B, for example, right, would be okay, we have free body diagram. What are the directions and magnitudes, right, for let's say the electric force? So direction and mag electric force. So we have this right here, this formula, this equation. It's the same thing magnitude wise. So the magnitude of the electric force is equal to, you know, the charge of that point times the magnitude of the electric field. And then, okay, we have values for that. So we just multiply negative 100 nanocoulombs. So converting to SI units, it's just times 10 to the power of 9 coulombs. And then times
Would it be negative? Would it be a -9?
oh yeah,
Yeah.
oh Jesus, I keep doing that. Thank you. So 2 times 10 to the power of 5 newtons per coulomb. These cancel out, just dimensional analysis. And what I got from that yesterday, oh not yesterday, Friday, was 2 times 10 to the negative 2 newtons. So one thing that they would like to ask you is, okay, we have a field, we have a charge, we have an angle, nothing is moving. What would the mass of this be? So say part C would ask you mass question mark. And given that all we have is a bunch of values and an angle, trigonometry most likely is going to help us. So we can say the tangent of theta being 15, is equal to opposite over adjacent. But the opposite of what over the adjacent of what, right? So imagine you just extend this tension line. What you get is the same corresponding angle, this 15-degree angle. And okay, you draw a little box here, just for visibility's sake. Okay, I just kind of eyeballed that very roughly. It should go to here, for example, right? FE. Okay. Opposite over adjacent. These aren't literal lengths, but we know that lengths are supposed to, the length of a vector is supposed to be proportional to its magnitude. So, L up, L edge. The opposite from this angle would be this right here, the magnitude of the electric force. So, okay, L adjacent to this angle. That's just this right here, the gravitational force. And Fe, we already have a value for that. Found that a second ago, so we can just leave that there. And we know that whenever, something has mass and there's a gravitational force, we know that the gravitational force is always equal to mg. There's a pop-up. Bruh. Okay, anyways. And it wants you to find the mass, let's say, right? So all you have to do is move stuff around, and then the mass should be equal to uh, Fe over G tan theta. And yeah, that is how you find such a thing in a setup like this. Um, oh, can you do this? Can you do this trig if the particle is not moving? If the particle was moving, the electric force and the gravitational force wouldn't be the tension components. Yeah. This particle is stationary. It does not move at all. So we're assuming everything to be in static equilibrium. If that answers the question.
I have a question about the electric force.
Yeah,
So it's negative 100 times 10 to the ninth coulombs for the Q value, but it comes out to be positive. Why is that?
comes up to be positive.
Like a positive 2 times 10 to the, what is that? 10 to the negative 2 newtons for the Fe.
Oh, oops. You're right. Yeah,
Oh,
that
okay.
should have a negative. Wait.
Because then in the
Yeah,
end,
you're
that
right.
wouldn't make sense though, because should you get a negative mass or it's tangent of 15, negative value 2?
Actually, yeah, this is a good chance for me to look through all the math I just did. Uh,
Is it because the electric field's moving to the left, so that's -2?
I
So
mean,
then,
yeah, if you wanted to encode direction into, the scalar representation, this technically would be, you know, I gave this as a magnitude, but it makes more sense to, encode the direction into it. So yeah,
Oh, that
this
makes a
should
lot
be
more
negative.
sense.
Yeah,
So
yeah, yeah, yeah.
then if you put that in, then it would come out to be positive, and then you have a positive mass, I think. Yeah.
Yeah. That way, the magnitude of a force isn't coming out to be negative, which doesn't make sense because the magnitude of a force should always be positive. Yeah, thank you for catching that. Am I clarifying everything for everyone so far with this problem?
Yes.
No more questions for this at all?
I'm good.
All right, perfect. Let's see. The second problem I went over, the
Actually,
rod
sorry, one
problem.
tiny question. Would the
Oh, yeah.
mass at the end be in kilograms?
Since I'm converting everything to SI units, yeah, should be kilograms.
Okay.
Am I good to go with the second one? Or the, second recitation problem I did? All right, perfect. So, all right, you have a rod, charged rod, and okay. X equals negative L over 2. And here, X equals positive L over 2. And then you have a point right here. And okay, here is the origin, X equals 0. And this distance right here, let's call this R. And okay, so um this problem involves linear charge density. Let's say, okay, end goal. We want to find the electric potential at this point. what is V at P? Right, V at P. Put triple question mark. This was a long problem. So, okay. How do we do this? Should we just say V equals K Q over P for this whole thing? How do you even do that? Right? So, I mean, to answer that question, I don't know either, unless someone has an answer. Besides just incrementing potential and just adding it up. So you have, a charge distribution within two bounds. And as you walk along this and add up increments, uh, let's see, this equation is still relevant, still very relevant, except, and also, K, they want you to do it like this, 4 pi epsilon, and then Q over R. If it's easier to add up increments of potential, then we can just go ahead and say dV is equal to this 4 pi epsilon of R dq q uh charge increment, right? And well, I should say big R. Let me not do that with notation. Big R, right? And okay, since we're scanning along this, right? Because again, like I said, we're finding a representation of the increments and adding up all of the increments. That is another word, term, phrase for integration, right? So in the integration, we're scanning from here to here, which means that R should define R to be big R, by the way. That should be the x value at the point P minus the scanning x, which just means that we are working with, well, let me just, I don't need that. X point R minus x. So R is equal to R minus x. A big R is equal to little r minus x. So to complete dV, well, complete it a step farther, I guess, that will give us 4 pi epsilon, 1 over 4 pi epsilon dq over r, big R. So r minus x. And okay, like I said, we're adding up a bunch of increments. We will use an integral. But if we're integrating over charge increments, what would the bound even, like what would the bounds look like? My answer is, I don't know. Doesn't really make sense to me. Makes more sense to convert this to x terms so that you're scanning over a distance, right? We already have two bounds, so we can go ahead and do that. And we know that charge density is equal to, a total charge divided by a length if we're doing a rod, right? So we can say a piece of this divided by a piece of this should give the same thing, because I need to specify the charge distribution is uniform. So if you take an increment of charge and divide it by an increment of distance, then you'll get the same exact thing. And as a matter of fact, uh, okay, why include lambda? Or why leave lambda in the math if we already have these things that we will know what they are, So you can say solve for dq. So you can, put in terms of x, dq would be equal to dx to this side, so q over L dx. Q over L dx, which makes the increment of potential equal to this. Over L dx are minus x, right? And like I said, total potential is what you get when you add up a bunch of little mini potentials across the rod. And oh, beautiful. We have an expression for, dv. So we just plug. And since we're putting it in terms of x, we will put the bounds on the integral. So it goes from negative L over 2 to L over 2. And, all right, just throw this in here. 1 over 4 pi epsilon q over q dx over L or minus x. And okay, this is messy. There's a lot of constants in this integral, and everything is multiplied. So you can just bring those out of the integral, pull them out. So you have q over 4 pi epsilon L, right? Integral. And then that leaves you with dx or minus x, right? Let me see if I'm if I missed anything. Okay, good. Of course, stop me if there are any questions. Otherwise, I will continue with the math. Just looking at this integral, just looking at this, the easiest way to solve this integral is u sub, in which case we would be saying that u is equal to r minus x. And then you take the derivative of both sides, du is equal to negative dx. And we have a dx here. So we're putting x into u terms now. So you just bring that negative over here in front of the du. That gives you dx. So you plug negative du straight here, right? And okay, x equals negative L over 2, x equals L over 2. Since we're putting the integral in terms of u now, this variable, this new variable, we should take that into account. We should convert these bounds. So let's say x1 is equal to, right? Let's say this is x1, this is x2. x1 is equal to negative L over 2. x2 is equal to L over 2, which means that u1 would be equal to, okay, r minus this, r minus x1, which would evaluate to r plus L over 2. And u2 would be equal to r minus this, so r minus L over 2. So now we can rewrite the same integral just in terms of our new variable, which should make it easier to solve because, what's the point if it brings us to the same level of complexity, right? So, okay, u1, u2, let me fix that. u1, u2, let's see. u1, r plus L over 2. r1 plus L over 2. And then u2, r minus L over 2.
For the bounds also, can you also just write like u1 to u2 for them
Oh,
since you're
yeah,
gonna
yeah. Yep, I can do that. If u1, u2. Actually, as a matter of fact, that makes it cleaner because, yeah, for the rest of the math. So, yeah, I'll do that. Dx, that's just negative du. negative du over r minus x. We defined that to be u. So we have u, and okay, if you guys remember, when you have a negative integral, you just flip the bounds. That's how it can eat the negative sign without you just, simply just erasing it and ignoring it. So this is the same thing as u2 to u1. It just reverses the scanning direction of the integral. So du over u. And they don't put this on the formula sheet, but what you'll see on a calculus formula sheet is that this turns into what I'm about to write. 4 pi epsilon L. And then the natural log of, the absolute value of u evaluated between the same bounds. u2, u1, u2, yeah, u2 to u1. And then, okay, what this means, in case anybody forgot, is you're taking this, evaluating it at this, or you're taking this, evaluating it at the top bound, and from that you subtract this same thing evaluated at the bottom bound. So, in other words, this. Oh, oops. And minus 2. Right? And, as a property of logarithms, when you subtract, these logarithms have the same base. So whenever they have the same base, and you have a logarithm of something minus that same logarithm of something else, you can just say that this is equal to the logarithm of this divided by this, which I'm about to write. Natural log of u1 over u2. And okay, putting everything back into x terms, well, we can just, this is mathematically correct, but this is, we have r and l over 2, L, negative L over 2. So we want to put it in terms of the values that the problem gave us. So we just plug back in. The natural log of absolute value of, okay, u1 is r plus L over 2, r minus L over 2. And if I didn't mess anything up, I should get the same exact thing I had from my notes yesterday. Yeah. Does that make sense to everybody?
Yes.
Right, I'm going to circle that in. Anybody have any questions about this? About this problem, this solution, any of the steps? Is this the hardest level question we can expect on the test? I mean, you know, this is the longest one. And I guess, I guess so. It'll be the hardest question because, there are different factors that make it that way. There's length of the problem. So, in all of this math, you could mess up a negative somewhere and the whole thing is ruined, right? So there's that in any long problem. But besides that, you have to remember this specific calculus property. Well, a few, you know, negative reversing the bounds of the integral and natural log, also the log property. So yeah, I guess there are more concepts that you would have to remember for this specific problem. Uh, let's see. How much different would this be if it were a negative rod? Well, if it was a negative rod, the math, everything is the same mechanically, except what you put into this Q is negative. It's just little plug and chug of the same exact thing. And okay, we have another one. Perfect. Do you have a Gaussian problem? Yeah, yeah. I don't know if you were here. If you weren't, it's recorded. But uh, we have. Let me go back to it. All right. We have this problem, right? And this, I guess. I expect one. I guess one of the problems it really will have. It will be a Gaussian problem. Uh, and yeah, this is it. Were you here for whenever I went through this process? If not, I can go through it again. Oh, okay. Would you like me to go through it again, or does this make sense as it looks? Oh, okay. So I'll just go over it again because when I got to this point of the math, I forgot to hit record. So I'll go over it again. It's asking, so you have a conducting spherical shell. So, you have this empty space inside. You have this reference point and two concentric spherical surfaces, right, outlining the conducting sphere shell. And the first part is asking what is the charge at the center of the sphere. So actually, I'll do it again. Right, let me get a piece of paper. So, let me redraw that. You have this and then this little point in the middle. Damn, that's horrible. Okay, okay, let me fix this. All right. So, uh, let's say you're given an inner radius and an outer radius. Oh, I just saw the message. Oh, yeah, yeah, no problem, no problem. I hope this video helps. All right, back to the problem. Part two, right? You're soon to be given those, for example. Um, at each like radius, there is a respective field strength. So uh, just put E1, E2, and here's an important detail to remember. Uh, the electric field strength. Okay, let me first say this. The charge is in the spherical shell, but because of the geometry, the charge kind of just, at least in a way that we can treat it in the math, it kind of concentrates to this center point where I'd like to specify there isn't a particle, a charged particle. There's nothing. It's just a point. So just a point. Okay, and the charge concentrates, you know, field wise. The charge concentrates in the center. And so it's asking us, yeah, the charge at the center of the sphere. So conceptually, before I do any math, what we're going to want to do is, it just makes more sense. It's easier to find, to look at this inner sphere, this inner surface area, because what we want to do is we want to find the charge enclosed within the shell, and the sphere to do the, to consider the radius for would be the inner one, right? And since the charge concentrates in the center, You can go be anywhere in between. You can take any radius in between this point and the inner radius of the shell, and the enclosed charged will not change. So Q and enclosed and charged. Q enclosed does not change. Q enclosed does not change from, let's say, R within, you know, 0 and R1, right? So we can just go ahead and start using Gauss's law, which tells us that, all of this is an enclosed charge here and, little constant. And okay, like I said, we'll be using this inner surface, this inner sphere. We just shade this just to better illustrate it. We will be working with this inner sphere. So along that sphere, maybe I mentioned this, maybe I didn't, the electric field doesn't change. Along this sphere, as long as we're keeping the same distance from this point, this central point where the charge is concentrating, the electric field strength does not change at all. So what we can do is we can treat it like a constant. You can say this, just pull it out from the integral, and you have this surface integral here, and then Q enclosed for epsilon. And this over here, this is just surface area. You're just adding up a bunch of increments of area. So you're just going to get a total area, a surface area. So E area surface. But we know, let's say we don't know the surface area for a sphere. Luckily for you guys, they put that right there in the formula sheet. So just gonna go ahead and put that right there. Oh, let me make this visible. All right. So 4 pi radius squared. So the radius would be this one, respectively, R1. And that's equal to, let me shorten that a little bit. Q enclosed over epsilon. Okay, we just want to find the charge at that central point. We know it's concentrating there, so we just solve for this. We bring this over here and we say, all right, oh, okay, to be clean, we move this to the front first and foremost. So we get 4 pi times epsilon E R1. That should give you Q enclosed. Let me make sure I'm not missing anything. 4 pi E. Yeah. So that, let's say this is A, this is B. That's A, right? So for B, the B that I put here. Oh shoot, no, hold on, no. Those are details. Never mind. Okay, sorry about that. Those are details, bullet points, just things to consider. So, the first thing is finding the charge at the center of the sphere. Mission accomplished. Now, we want to find the excess total charge, the excess. And what does that mean? That does not sound like it makes any sense. Well, it does. Because if we remember that these surfaces have charge distributions over them, if you look at this sphere around R1, that encloses a different charge than the charge enclosed within this bigger sphere, this bigger concentric sphere. And if you find the differences, if you do this same exact thing for each radius and you find the difference, then you just find actually the charge enclosed within the shell itself, the shell's charge. So without doing all this math, because we're working with the same exact thing geometrically, and it's mechanically you're gonna do the same thing to find you know the enclosed charge with respect to each sphere. So we already came up with a formula for it. Let's just use it. So okay, you see E here, right? That's E1 because that's just that corresponds to R1, right? Okay, so Q excess is equal to Q enclosed 2 minus Q enclosed 1. And really, that's just, you can factor these out from whatever you're going to subtract. Uh, these are just, these don't change. You get is E2 R2. Okay, I noticed a mistake, but I'm going to keep rolling. Minus E1 R1. The mistake is that this should be squared, this should be squared, this should be squared. Sorry about that. But does that make sense? Did I go too fast? Was there anything that kind of seemed arbitrary in any explanation? Oh, perfect. Great. Okay, how's everybody feeling about the test? Given this session, I will post the video, of course. Oh, better. Okay. Hey, that's what I'm here for. If anyone has any questions, I'm gonna stay, for this goes until 4, so there are 10 minutes left. So whoever wants to leave, feel free. Of course, it's a little practice session. This is no attendance, no grade to this. I'm just helping you guys out through these problems. So, okay, let's see.
Thank you.
Oh, yeah, no problem. Of course.
Bye-bye.
I see. Let me scroll up. There's a question. Do you have any idea of some specific practice problems we can go back and review that would be helpful before the exam? Uh, the cherry problem is a good one to think of as well. I'd recommend that one as well. Yeah. So this is as close as I can get to what will be in the exam. Anything related to potential energy and electric fields? Yeah, that was the. I'll bring you to that problem. It's the third one that I did before I went over the recitation problems that I did, which are also modeled from the test, or modeled to be similar. But yeah, this specifically, practice this. You'll be in good shape for the test. They'll more than likely you're going to be given uh some expression in terms of x and y for potential energy, and yeah, you take derivatives and stuff and plug in numbers. Actually, yeah, this is potential energy. There was a potential problem I did. And let me see if there are other questions. All right. Well, I'm gonna sit back, and anyone that has any questions, oh, perfect. Is there anything else I should be studying? Or if I know how to do all of these problems thoroughly, should I be okay? Yeah, yeah. Know how to do these problems, you'll be in very good shape for the test.
How soon after this before will the recording be available to watch?
Sorry, what was that?
How soon after the like call ends will the recording be available?
Okay, I'm not the best with Canvas, but I will, as soon as this meeting ends, I will work on like publishing the video.
Okay.
So if I really, if I really flop, then you'll probably see it 30 minutes later. Shouldn't be that hard. It's just a
Okay.
file. Most likely, I mean, the easiest way I can imagine is just putting it on, downloading it, putting it on an announcement or something if permits me to put that kind of file there. Oh, let's see. Is there anywhere we can go to find more practice problems like these? The problem sets, I will say, these problems are also pretty similar to what I've seen in your guys' problem sets. So, with that being said, the the test bears the test will bear some resemblance to the practice set. So if you can go back and practice the problem sets, uh, power to you. That would not be a waste of time. You will, you know, you know, arm yourself with good ammunition for the test, I guess. If that's how to word it. Yeah, yeah, no problem. Anybody else have any questions, concerns about the test? Uh any suggestions I can give besides those already given? I mean, I could give them again, but actually, let me stop the recording.